So with distributions out of the way, we're going to start talking about what are called our measures of central tendency in section 2.3, where when we're talking about central tendency, it's kind of a, I don't know, some might say pretentious, but that sounds a little bit derogatory. It's a bit specific of a way to talk about what's essentially an average. We're trying to figure out what happens to most of the data. If we're going to think about just taking some random representative out of the data set, about where should it be without much other consideration. And the place we're going to start talking about this is with the mean. And the mean is probably what most people think of when they initially think of an average. In particular, if you're looking on Excel, for example, when you compute the mean, you just tell it to compute the average. So it's very often thought of in specifically that way, where a lot of times people call it the arithmetic average. And for us, it's not going to be anything hopefully new. I mean, if you've probably seen computing the mean before, computing it as an average, it's just we have a little bit of extra notation here. So we're taking the same sort of idea to get the mean that you're probably used to. You look at all of the values in your data set, you add them all up, and you divide by the number of values in the set. Where when we're doing that in this case, we have this specific notation here that we work with, where we are taking the sum. That's what that sigma, the capital sigma of something means, take the sum of, and then we divide it by the number of things. Where, because we're talking both about populations and statistics, we have slightly different ways to talk about it. When we talk about a sample, the sample mean is denoted x with a little line over it, that's read x bar. Meanwhile, when we're talking about a population, we're looking at the population mean. We are talking about the Greek letter mu. And this hints at a pattern we're going to be seeing a lot more throughout the semester, but especially in our next section, that when we're looking at sample and population things, we usually denote the sample term, as it were, with an English letter that might have an accent, and the population term gets a Greek letter. Why that's convention, I'm not entirely sure, but it's how we generally do things. And in either case, the formula isn't actually different here. There will be some subtle differences in other formulas, but for now, the main thing is just that we're specifying the context in which we're computing the mean. And to rebuild some connections here, let's look at a quick example, where for this example, a surveyor collected the heights of a third grade class at the zoo. Surveying is a hard job, to be opportunistic. And the data is as follows in inches, where we get heights of 46 inches, 44 inches, 54, 168, 49, 43, 46, 48, and 44 inches, where what we want to do here is take this data set and compute the mean. Well, here we're looking at the heights of a class of third graders. We're going to take that as a sample of all third graders. So we're going to note this with x bar, and we're going to take the sum over our values and divide it by the number of values. It's nothing new, just it's a little bit more of a mathy notation, a little bit more language here. And to do this, we just take those values that we have, which I'm going to put in ascending order for no good reason. 43, 44, 46, 46, and I'm going to run out of space, so I'm just going to skip to the end here, where the last couple of values are 54 and that mysterious 168-inch third grader. And because we have 9 of these values, we divide by 9, and we run that computation, where later on I'm going to show you a little bit in here with how to do that in the calculator. This is a pretty simple one though, so it's not as big of a deal. But anyway, you run that kind of computation, And what you'll get is an average of 60.2 inches. Conventionally, with the mean, you round to 1 decimal place more than the data set, but it's not a convention we observe too rigorously in this class. Anyway, this says that the average third grader is 5 feet tall. Now, it's been a while since I was in third grade. It's probably been a while since any of you were in third grade. But I don't remember that many third graders who were 5 feet tall. And in fact, there's something a bit off with this data set. Hopefully, you guys have been thinking, 168? How is there a third grader that's 14 feet tall? And the answer to that question is, well, realistically, there isn't. Because our surveyor wasn't very good at his job. And as a result of our surveyor not being very good at his job, when he collected that sample, he threw in a giraffe. He was at the zoo after all. But unfortunately, because the surveyor didn't do very well, the mean got dragged away. In this case, that mean of 62 is kind of meaningless for this data set, even with that extremely unusual value. It's lower than the very high end, and it's much higher than where a lot of the data is. And this points out an important weakness of the mean, that if you have outlying or incorrect data, you have unusually large or small values, they can drag the mean pretty effectively away from the center. And in that case, the mean doesn't really tell us anything meaningful. It's not a meaningful mean. Point is, that weakness to outliers is kind of a central weakness that we can have when we're measuring the average using the mean value.